Hello everyone. Today I'm going to show you how to construct a transmission line resonators using field power ADS. Well, we can form a single mode resonator, and we can also play some trick to construct a dual mode resonators without changing the electrical length of the transmission line. So first we drag in the input and output ports, port 1 and port 2. So we have the predefined 50 ohm system impedance here, and we need the capacitors to provide the necessary coupling from the port to the resonator. And we need a transmission line, of course, to construct the resonator. So now we form the connections. So let's define the values of the capacitors with the random value, let's say 0.5 picofarad. And the transmission lines has 50 ohms impedance. Let's say we want to resonate at 1 gigahertz, or we can choose from this prefix here. And a conventional resonators, it should have 180 degrees. In other words, it's a half wavelength resonator. So I'm lazy to drag in a new capacitors for the output coupling and key in the values. So I can use the shortcut key Ctrl+C and Ctrl+V to copy and paste the same capacitors for the output coupling, since it's a symmetrical structure. Now we are ready for the simulations. So we go to the setting page and define our simulation setup. Let's say we want to look at the simulations starting from 0.5 gigahertz to 1.5 gigahertz, since our resonance is at around 1 gigahertz. So now we are ready for simulations. Let's click on the simulation button here. Here you go. So we have one resonance close to 1 gigahertz. So the shift of the resonance is simply due to the coupling C, causing the shift of the resonance to the left. So what we're going to do now is how we're going to play some trick to form a dual mode resonator. So as we know, this is a half wavelength resonators. So what I'm going to do is I'm going to split this transmission line into two. So I'm breaking the connection here, and I change this to half, which is 90 degrees. Then I'm going to copy and paste the same transmission lines with the same electrical length. So in total, we're going to have 180 degrees electrical length. So we didn't change the electrical length at all. Theoretically, it shouldn't change the response. Okay, so nothing changes on the response here. So how are we going to form a dual mode resonators without changing the electrical length? Here is the trick. So we drag in an inductor here. So we connect the inductor to the center of the schematic or of the circuit, and we need a ground for the inductor. Well, so we're going to define a random value for the inductor as well. Let's make it 1 nanohenry. Okay, so what will happen? Let's find out. See, so now we can see two resonances at the same time by simply adding this inductor at the center and connected to the center of the circuit. As you notice, this resonance remain at the same locations as the original one, which is at 0.91 GHz, and you have an additional resonance at 0.795 GHz simply due to this inductor. So if we want to move these two resonances close to each other, we can change this inductance value. Let's say we make it 0.5 nanohenry. Here you go. So this resonance is moving closer to the original resonance. So if you want to form a very nice bandpass response with two resonances, so you can move this closer again by lowering the inductance value 0.2 nanohenry. See, so we have a very simple two-pole bandpass response with a single half-wavelength resonators. In other words, we can have the same physical dimensions of 180 degrees electrical length. By adding an inductor, we are able to produce two resonances rather than one. So this helps to reduce the circuit size or the layout in practical implementations. In the next video, we're going to show you how to transform this into a real implementations using microstrip or other transmission line implementations. Thank you for watching.